Here's a velocity time graph for an object falling with no air resistance. We should be used to this by now. Strictly speaking, if we're calling it a velocity time graph rather than a speed time graph, we should make it clear that the vertical axis is measuring speed in a downward direction. More about this in the section on vectors. It starts with zero velocity and then the velocity increases uniformly. What would the graph look like if we didn't drop the object but threw it down vertically? Well, it would accelerate at the same rate, so the gradient would be the same, but it would start with an initial velocity, say here. Throwing it down harder might give this line. The acceleration can be calculated from the first line by finding the gradient, differentiating, and it has the value 9.8. Its unit is metre per second from the velocity axis, per second from the time axis. So the acceleration is 9.8 metres per second squared, which is what we already knew about motion under gravity. It has a constant value, so a graph of it would look like this. But the point we're trying to make in this video is that all three situations, the dark blue line, the green line and the light blue line, give the same acceleration graph because they all have the same gradient. If we're given one of the velocity time graphs, we can generate the acceleration time graph. But if we're given the acceleration time graph, we cannot tell which of the three velocity time graphs it came from, without more information anyway. In fact, there are an infinite number of velocity time graphs that could be made from the acceleration time graph, all having the same constant gradient, but having different intercepts. The intercept in this case has a physical meaning. It's the initial velocity, which we can call v0. A subscript of 0 often means at time 0. Now the equation of these three velocity lines is v equals 9.8t plus v0. And if you're not sure that you understand where this comes from, you can think about that as an inevitable consequence of what acceleration means, or you could compare it to the equation of a straight line, y equals mx plus c. But what does that have to do with integrating? Well, if we try to get the velocity at time t from the acceleration graph, the area under it will give us this extra velocity of 9.8t due to the acceleration, but it will tell us nothing about the initial velocity, v0. If you do know the value of v0, then that in effect locks the infinitely many possible graphs into the one corresponding to your initial velocity, giving you, for example, the green line rather than the blue ones.